Hi, welcome to today's Hackerpraktikum. I'd just like to make a quick announcement before we start with the talk. For those who don't know me yet, my name is Carsten Tellmann. I work for G-Data, that's a local antivirus company, and we are sponsoring this course. And in addition to this course here and the talk, we offer a small evening event. Basically, it means we offer some food and drinks and a cozy location where we can have nice discussions, and if you like to have the opportunity to talk about the talk's topics with a speaker in detail, or just like to talk to some of the guys working in the antivirus company, you're all welcome to join us. And yeah, if you have any questions to this event, just come to me after the talk and I can explain in detail. And now, yeah, I think you will introduce yourself. So
okay. Thank you.
have a nice talk.
Okay. Good afternoon, everyone. Thank you for coming. Can the people at the back hear me okay? Yeah? Great. Okay, so today I'm talking about timing attacks in the browser. So just first of all, just a few slides about myself and about the company I work for. So I'm Paul Stone. I work for Context Information Security in the UK. I used to be a web developer, and now I'm a security consultant. My day-to-day job is mostly penetration testing, testing web applications and so on. And my kind of hobby is this browser research. So the stuff that you see today is the things which I do in spare moments in between doing tests and writing reports and things like that. Yes. Okay, so Context is a company that I work for. We're a security consultancy, and we're based mainly in the UK. We also have an office in Dusseldorf, and we have an office in Australia as well. We have clients from all over the place, some large banks and government organisations. And we do a whole bunch of stuff. So I mainly do penetration testing, web application security, but we have guys doing lots of other interesting stuff, malware, testing mobile devices, and all sorts of things. So today, I'm going to be talking about a few things. So at the start of the talk, I'm going to be covering just the basics of timing attacks. I'm going to be going over some older vulnerabilities, but things that are still interesting. I'm going to cover a few, I'm going to deviate slightly from timing attacks and talk about a few other things, and you'll see why that is later. And then I'm going to take those vulnerabilities that are now fixed in the browsers, and I'm going to show you how we can bring them back using timing attacks. And we have some O-days as well. So hopefully you enjoy it, and we'll get started. So timing attacks are a subset of side channel attacks. So side channel attacks cover all sorts of things. So these are ways of indirectly finding information or secret information that's stored on some device or on some system or something like this. So we have power analysis, so things like the MyFair, smart cards and things like that. So guys have been trying to reverse engineer those, trying to pull the keys off them, try and break the cryptography. There's things like emissions monitoring or VANET phreaking, and Tempest is the kind of standard that the US government has to try and prevent that. So this is the kind of thing where your computer and your monitor will be emitting all sorts of radiation that can be monitored, and potentially someone with a directional aerial can tell what's going on inside your PC from a few hundred meters away. But today, of course, we're talking about timing attacks. And yeah, so what is a timing attack? So speaking very broadly, not to do with browsers in particular, but with any timing attack, we have a black box. So we have a black box there, and we can put input into it, and we get some sort of output. Now, often the output itself doesn't tell us very much. Maybe the output's always the same. Maybe it's not very interesting. But what we're interested in is some sort of secret inside that black box. Now, the black box could be a device, it could be a program running on your PC, or it could be a client server system, basically any closed system that we want to be able to see into. So with a timing attack, we give this black box some input, and at some time later it gives us some output. And we can time how long it is between the input and the output. And we can try this for different inputs, so we can try sending different inputs and seeing what happens, seeing how the difference is in the timing. So we compare our inputs to the time it takes to process that input, and somehow we can put that together and infer some sort of secret information that's stored inside of that system. And that's what we're trying to do with a timing attack. So moving on to web browsers. So the core of security in every web browser is this thing called the same origin policy, which I'm sure quite a lot of you are familiar with. So the same origin policy is what protects the data from one website you're logged into, protects it from other malicious websites, other windows that are open, other tabs. And the crux of it is that one domain cannot access, cannot read, or modify any data from another domain. That's a theory, but of course there are always exceptions. Web browsers have been around for years and years and years, and there's all sorts of strange rules and odd things that have cropped up because of the way that browsers have grown organically over the years. So for example, websites can load images, scripts, style sheets from any other site. And when it comes to timing attacks, we have, when you load a style sheet or an image, we have these events that come back, these callbacks, so on load and on error. And we'll look at those in a minute. We also have iframes. So any website can load any other website inside of an iframe if the website doesn't have any click tracking protection. And when the site loads in it, we have an onload event that happens. So we know that the same origin policy prevents us from the outer website from seeing what's inside the iframe. But the one piece of information it has is the onload event, so it knows how long that page took to load. And then there's various other things, ways that two domains can communicate. So things like post message, submitting forms, XML, HTTP requests. We're not going to be looking at those today, but these are just, there's lots of little ways in which websites can pass data between each other, either because they want to, or because there's some malicious intent that's happening. So we're talking about timing attacks in the browser. So how do we time something in JavaScript in the browser? It's very, very simple. So there is an object called date, which has a function called now, and this will just return the current time in milliseconds since the Unix epoch. And the precision of this function is in the low milliseconds. It depends what operating system you have, but typically anywhere between 1 and 20 milliseconds. That's the kind of resolution of this timer. So to start with, I'm going to cover some very simple techniques, some very simple timing attacks, and these are things which are inherent in the way that web browsers work. These aren't really things that can be fixed, but they let us do some very interesting things nonetheless. So let's say that an attacker wants to discover whether a user is logged into a particular website. So the premise here is that the user is logged into a particular website, and at some point later they visit a malicious website. Obviously, they don't know it's a malicious website. It may look fairly innocent, but they've visited this website, and the website can then run some JavaScript in the user's browser. So what if this malicious website makes a request to this URL, bank.com/myaccount? So if the user is logged in, then this page will return a 200, OK, and that takes a certain amount of time, say 1200 milliseconds. What if the user is not logged into the website? In that case, you would maybe try and visit the My Account page, but because you're not logged in, the website would redirect you back to the login page. So in this case, there are two HTTP requests that have happened, and together, maybe they take less time than actually viewing the account page. So because of the same origin policy, the malicious website that is making these requests can't tell that visiting this page got a 200 response or a 3OT redirect. It can't tell that. The only thing it can tell is how long this request took to come back. So a very, very simple way of making an HTTP request from a web page is to use the image object. So obviously image is meant to load images, but we can use it to make an HTTP request. When you give it the URL at the bottom there, so image.source equals whatever URL you like, at that point the browser doesn't know whether the URL you're sending is going to come back with an image or not. And when the server does respond, in this case it will respond with an HTML page. The browser will say, hang on, this isn't an image. So it will trigger the onError callback. And the JavaScript can time the delay between setting the source, between sending the request, and between it coming back. So that variable t there, that will be the time in milliseconds that it took for the response to come back. So presumably the attacker has tried this out. He knows that the My Account page will take longer to come back, and therefore he can tell that the user is logged into this website. So there's various things that you can do using this kind of technique. You can obviously, like we said, tell if a user has visited a site. The JavaScript could test lots and lots and lots of URLs in a pretty short space of time. So they can tell if they've visited it, if the user is logged in. And you can also do some more complex things. So if the attacker studies different pages on the website, they can see that some pages might take more time or less time depending on certain parameters you send to it. So in some sort of shopping website that you might be logged into, you might be able to try different product IDs, and maybe with a URL like this, if you give it a product ID of something you have purchased, it might take more time to come back than a product you've not purchased. So an attack like this could try lots and lots of product IDs and try and tell which product the user has purchased. So a slight variation on this attack is a cache timing attack. So every web browser has an HTTP cache, and the point of it is to speed up your web browsing, so it will save responses from HTTP requests, so that if you visit the same site again, it already has that, it doesn't have to load it back from the server. So if an attacker wants to see if the user has visited some sites, they might pick a URL, perhaps an image, like the logo of the site, something that's would definitely be in the user's cache if they had visited this site. So the attacker's website would make this request for the image, which would sent, and if it's in the cache, obviously that request won't go to the server, it will come straight back from the browser's cache, and that'll be a very short amount of time. And for another URL, if it's not in the cache, this time it will go to the server and then come back, and it will obviously take longer because it had to go over the internet. But then after that, obviously that image is then cached. So this isn't an attack that can be repeated because the attack itself will alter the user's cache. So there are some problems, some obstacles to overcome if someone wants to carry out a timing attack. So obviously because if we are dealing with timing attacks that go over the network, there's latency, there's jitter, things that can give imperfect timings. And then, of course, sometimes the attacker doesn't know how long a particular thing might take. So when they run it on their machine, it might take in a certain amount of time, but when the user runs it, it might take a different amount of time. And that can be also down to all sorts of variables like the speed of the user's computer, speed of their connection, and things like if there's other programs running on the user's computer, or how busy the server is. So there are ways to overcome that, and the best way is really to do lots and lots of measurements. So instead of making a particular request or taking a timing just once, the attacker might take it lots and lots of times and take an average or median. And if you're mathematically inclined, there are much more powerful statistical methods, which I won't go into because I don't know how they work. But yeah, so those can help sort out latency and jitter and things like that. And also, it's possible that the attacker's code can perform some sort of calibration, so it can do a test against on a subject that is known, and then when it's testing against some kind of unknown, with some unknown resource, then it has something to compare it to. So now I'm just going to go over some old vulnerabilities, things that have been fixed, but they're quite interesting nonetheless. So this is something that was fixed in web browsers a couple of years ago, but was unfixed for years and years and years. Pretty much since web browsers had JavaScript, this was possible. So we have some links at the bottom here, pointing to different websites, and the attacker wants to know whether the user has visited those links. So your web browser has a history of all the websites you visited, and obviously CSS can be used to color those links differently depending on whether you have visited them. So in order to find out if you have visited these sites, the attacker could do something like this. So these style rules apply to each different, one to each link down there. And what this says is, if the link is visited, then set the background image of that link to this URL. In this case, it's the URL. It will make a request to the attacker's web server and will ID that particular link. So each link has a different ID, and the attacker can then find out if you have visited that. So background image is one way to do it. You can also you could also do it with JavaScript and the getComputedStyle function, which returns a list of CSS rules for a particular element. And this was a very interesting technique because you could test hundreds and hundreds and hundreds of links in a very short space of time. And it wasn't exploited in the wild as well. There's this paper here which covers some. They essentially test a whole range of sites. Kind of spied them to see if they were using this technique, and they found quite a few sites that were surreptitiously testing users' browsers to see what other sites they'd visited. But this is now fixed. There's a link at the bottom there. So Mozilla were the first, Firefox was the first browser to fix this leak, and all the others followed. That link at the bottom explains how it works, but essentially there are certain CSS rules that you can no longer set on visited, using visited, so you can't set background colors or background images, you can't change the size of the elements, and it's quite restricted now, so this is fixed. Now frame sniffing is a different attack. This is something which I blogged about earlier in the year. You can read about it on the Context website if you like. I'll just take you through it very briefly now. So frame sniffing uses iframes, and it allows an attacker website to tell what IDs are in the HTML of a web page. So on the right here, you've got a Wikipedia page, and each heading has a different ID. And if you append that ID onto the URL, so you put hash and then the ID, the browser will scroll down to that particular link. Now, the frame sniffing attack abuses this functionality, and it uses nested iframes. So how it works is that the attacker site has the target website in a very, very, very big iframe. So it sets the width and height to be very large so that the site itself has no scroll bars at all. So maybe 10,000 pixels by 10,000 pixels. It then puts that iframe inside of another iframe, a very, very small iframe. And because that iframe is part of the attacker's domain, the attacker has control over it. So we have a very large iframe inside a very small iframe. And how the attack works is that the attacker will append this ID onto the end of the URL inside the inner frame. And if there's an element that matches that ID in the inner frame on the target website, the browser will try and scroll to that link, to that element. Now, because the inner iframe is very, very large, it has no scroll bars, that frame can't scroll. So instead, the browser looks at the parent iframe and scrolls that instead. So the parent iframe, which belongs to the attacker's domain, is scrolled, and then using JavaScript, the attacker can read the scroll position of that frame. So why might you want to do this? So I looked at SharePoint, although this could apply to many, many systems. So SharePoint is a Microsoft product that lets you store documents and search for documents. And this is the URL that you use to do a search. So when you type in a search on the website, you search for a particular word, and it will go and search for all the documents that have that word in it. And when the page comes back, if there are results, like any kind of search engine, you'll have this pagination at the bottom, and each link there will have an ID. So the frame sniffing attack can load this URL in an iframe, search for a particular term, and then see if those IDs are present on the page. And if they're not present on the page, then we have a different ID there, so CSR no results. So the frame sniffing attack can do a search and see if there are matching documents. Now I've got a video which shows how this works. Right. So yeah, this is SharePoint. This is the documents that are stored in SharePoint. So this could be on an intranet, and because of the way web browsers work, any page from the internet can load that site in an iframe. So this is the attacker's website, which looks innocent, obviously, but behind the scenes there, it is loading this URL, which presumably the attacker knows. It's loading it into an iframe. And then it can start doing these searches. Now, because the SharePoint is hosted on a local server, those requests can happen very, very fast. So this is the attacker's view of things. So the web page that the victim is viewing is communicating with the attacker's web server. So the attacker can now put in the URL of the SharePoint server and then do a search for a particular term. So this is a blind search. So what's happening here is that this page is doing a wildcard search. So it's searching for A star, B star, C star, and then when it detects an ID on the research result page, it detects that it's got a result. So if it has a result for A, for example, it will then start searching for A, B, A, C. So this is kind of skipping to the end here after a few minutes, and this attacker's pulled out all of these words. These are words that are in the file names of documents, and it's got things like company names, kind of information that might be interesting to an attacker. And this is a slight variation of this. So this just allows the attacker to type in any search term they want. So they might use words that they found from the blind search, so company names like Acme here, and so they can do the search and they can see how many results came back. So the first one there came back with 31 to 40 pages. So the pagination link at the bottom, there were 3 links or 4 links, and then you can see results that didn't come back. So yeah, I won't show you the whole video, but essentially I kind of skipped to the end. So the attacker kind of builds up this search gradually using kind of Boolean terms, and eventually it's now searching inside of a document, and they find a bidding price. This is fictional, obviously. They find a bidding price for some sort of company acquisition or takeover, and at the end they find that they're going to acquire a company called GarCorp for £35 million. So yeah, this is the frame sniffing attack. So yeah, like I said, if you want to understand this in some more detail, it is on our blog. Oops. But this is now fixed. So I reported it to Mozilla first, and they fixed it at near the start of last year. And now Chrome, Safari have fixed it. So this attack is no longer possible. And the third, just one third thing before we get onto the O days and the timing attacks. So this, so WebGL which some of you probably have heard of, is something which is in Firefox, it's in Chrome. I don't think Microsoft will ever support it. So it lets JavaScript run OpenGL code in the web browser and create 3D scenes inside the browser. But the particularly interesting thing, well, the two interesting things, is that, first of all, it is possible from JavaScript to write shader code, and this is code that runs on the user's GPU. And secondly, it's possible to, or it was possible, to load images from other domains, load them into the 3D scene as textures. And what was then possible was to write a shader which would run on this texture, on this image that has been loaded from another domain. And this is pseudocode, but very, very simply, the shader could read the pixel value. Now, this pixel, the values weren't accessible directly from JavaScript, but this was a timing attack in this case. So it's possible in the shader code to run a loop and then to exit that loop early depending on the brightness of the pixel. So if the pixel was black, it would maybe run just one iteration of the loop, and if the pixel was white, it would run a few thousand iterations, and so the shader would take longer to return back to the JavaScript. And I've got a little demo that shows that. So this is a demo that my colleague James Forshaw put together last year. So this shows how an image from another domain, which shouldn't be accessible due to the same origin policy, or it shouldn't be possible to read back the pixel values. So the WebGL, the shaders, can be used to read those pixel values one at a time and to steal that image from another domain. So this is fixed in Chrome and Firefox now. So this image that's loaded here is actually on the same domain, but this shows roughly kind of how it worked. So this is quite an interesting timing attack. But like I said, it is now fixed. Okay, so moving on now to talk about graphics in the browser. So this is the main thing that this talk is about. So the first thing that I'm going to introduce is this thing called request animation frame. This is something that's new. It's kind of part of the whole HTML5 spec. And it's something that was first implemented in Firefox, and now Chrome and I think IE 10 support this now. And it's essentially a function that calls back to JavaScript. And it's like set timeout. So set timeout and set interval are functions that will pause or wait for a certain amount of time and then call back into a function. So they can be used, so set timeout, set interval can be used to do things like animations on web pages. But request animation frame is slightly different, and it's more interesting because request animation frame is synced with the way that the browser draws each frame. So if something is animating on a web page, the browser will be repainting. So if you scroll a web page or if you click a link, obviously the browser has to redraw that page. So request animation frame is something which will call back. It will call a user function just before the next frame is rendered. And it is called up to 60 times per second. And this JavaScript here uses request animation frame to measure the frame rate. So it's very, very simple code there, but essentially what you end up with the variable t there, and that's the time it took since the last frame was rendered. So if everything's running very, very quickly, the browser will run at 60 frames per second. But if there's something which is taking a long time, if there's some complex graphics, then they can slow down the frame rate of the browser, and you get a lower frame rate. So the JavaScript can now measure the frame rate that is being used to render the web page. So this is potentially interesting for doing timing attacks. So like I said, ideally, browsers run very, very quickly, but things can slow them down. So what will take a browser, what will take us down from the 60 frames per second? So one thing is what's called in browser terminology is reflows. So a reflow happens whenever the structure of the page changes. So any time that JavaScript inserts a new element or removes an element or changes the size, the browser has to calculate the position of everything on the page that's changed, and that can take a bit of time. Aside from reflows, browsers also support some very interesting graphics features now, so they can do transparency. CSS transforms is something that's relatively new, and you can use that to rotate items on the page. You can make them bigger or smaller. You can do 3D transforms as well, so add perspective to elements, and that can take some time. There are shadows as well, so you can have shadows on text, you can have shadows around elements, around boxes, and depending on if these are done in software and hardware, they can really slow down the page if you have lots and lots of shadows. And then there's things like SVG filters, which we'll look at later. And of course, JavaScript itself, if there's lots and lots of JavaScript running, then that can slow down the page. Because every web page is single-threaded, if there's some JavaScript running, then all rendering will halt until the JavaScript is finished. That's leaving aside web workers, which is something new, which allows you to run JavaScript in a separate thread. But in the main, any time JavaScript is running, it will block the rendering and slow down the frame rate of the browser. So these things are great if you want to carry out timing attacks, things that can slow down the browser and things that we can measure. But of course, browsers are getting really, really fast these days, and there's this constant battle to optimize and to make them faster. And every new release of every browser, they say we're the fastest, we can do this benchmark quicker than that browser, and everyone invents their own benchmarks to prove that they're the fastest browser. So the things that can prevent the frame rate from dropping are things like hardware acceleration. So these days, every browser now does some rendering on the graphics card to speed things up. Drawing of lines, drawing of text, or applying effects and transparency to things, that can be done on the graphics card. And things like composited layers. So if you have an element on a web page that's on top of another element, then the browsers now render those separately. So if you have something in the background that's scrolling and there's something on top of it, it can keep each layer separate. So if one layer is changing but another layer isn't changing, in the past the browser would have to repaint the whole scene, but now it can keep the layers separate and just redraw the one layer and then put them back together on the graphics card. And this speeds up rendering. And there's all sorts of optimizations, software optimizations that the browsers are doing to make their browsers faster. So if we're trying to be mischievous and trying to do some timing attacks, and these things can get in our way, and we want to find ways to avoid these. So how can we avoid these? How can we get around all these optimizations that are preventing us from doing these attacks? So as much as browsers try and do hardware rendering, there's always situations which they will fall back to software rendering. So there are, and every time there's an optimization, by its nature, any optimization will also have edge cases and corner cases and things which will cause an algorithm to run slower than it's intended. So most of the time, software engineers will try and optimize for the common case, for the things that most web pages are doing. So if we can do things that are unusual, do things that are a bit different, that the developers didn't expect, then we can cause things to slow down. And of course, there's code that's not been optimized. So of course, with a timing attack, we're trying to see these differences. So we're trying to run different things and see if we get the timing difference. So how could we use a request animation frame? How could we use this to carry out a timing attack to get some data, to get some secret information, some private data that belongs to the user that the same origin policy is trying to prevent us from getting? So this is talking at a very abstract level. This will make some more sense later on, but at a very broad, a very high level, with a timing attack, we want to find some resources some things which we're not allowed to see because of the same origin policy. So we find these resources. And then we need to find a function, something that takes that resource, does some processing on it. And because we're looking at the graphic stack, that function needs to have some sort of effect on the rendering of the page. So it needs to call something to redraw or to reflow. And it needs to take a variable amount of time, depending on the resource that we give it. If it always takes a constant time, then that's no good for a timing attack. And the time it takes needs to be measurable as well. So if you remember, I said that the date.now has sort of milliseconds precision. If the time that some particular thing takes is smaller than that, then we can't time it. We can't tell the difference in the timing. So this is why we're trying to slow things down, why we're trying to de-optimize the browser so we can measure the time that these things take. So this is a very rough outline. This is kind of like a template of how we could use request animation frame to do a timing attack. So at the top, we have an array. So there are R's there. So that is an array of the things. We don't know what they are yet, but the things that we want to measure. And then we have a second array, an empty array of the times. So we will be filling this with the time that each resource took to process. So then we use request animation frame to do a kind of loop. And because JavaScript is kind of asynchronous, it's not a for loop, but it's a callback loop. So request animation frame takes a function. In this case, it's called step. So we call request animation frame just before the next frame is drawn. It will call our function, and it passes a parameter, which is the amount of time since the last frame. So we can calculate that time difference, add it to our array. We can run this function, whatever it is, on our resource. So we run the function on every resource, so once every frame, and then we can tell how long each frame took to render, how much it slowed down for each resource, and hopefully we can tell something about the resource based on that. So we looked at some vulnerabilities before, some things that have been fixed, and now we're going to show how we can use timing attacks to resurrect these vulnerabilities. So we looked at frame sniffing. That was quite a fun attack. I reported to the browser vendors and they fixed it, which is, that's no fun. So the way they fixed it was this. So the frame sniffing attack happens when you have an iframe and you change the URL of that iframe to add this anchor tag, this hash tag onto the end of the URL, and then the frame scrolls. So the frame sniffing took advantage of the fact that the scrolling will look at parent frames as well. So if the frame that has the site in can't scroll, then the browser will look at the parent frame and try and scroll that instead. And that's how the frame sniffing worked. So the fix for that all the browsers implemented was to prevent the parent site from scrolling, and that prevents the attacker from being able to read the scroll position. But the actual scroll itself still happens. So when I navigate to an anchor in an iframe, if that ID exists on the page, then the browser will scroll down to that point on the page. So when the iframe scrolls, then the browser has to redraw the iframe. It has to render the new content that's appeared when the scroll happens. But if I navigate to an anchor that doesn't exist, then presumably nothing's changed. There's no scroll is going to happen because the ID doesn't exist, so no redraw happens. So can we detect that redraw when the browser scrolls? Can we detect that scroll has happened through the redraw? So how might this work? So first of all, we load the site into an iframe, and then the trick is to overlay that frame with something that's complex, some complex graphics that will take the browser some time to render. So then we navigate in the iframe, we change the URL to have this ID on the end, and then we call request animation frame. So what will happen is that the browser will then look for that ID on the page, and if it decides to scroll, it will redraw it. And then when our callback happens, we can tell how long the browser took to do that redraw. So if the anchor exists on the page, the browser will take some amount of time to render it, so the scroll will happen. And if the ID didn't exist, then the browser will not redraw the frame, no scroll happens, and presumably it will be a lot quicker to render the frame. So I have a demo of this. Okay, so let's see. I apologize, this demo didn't look more flashy. I didn't have much time before this talk to make something that looked kind of cool or anything. But this is it. So the complex thing we're putting on top of the iframe is a text. It's some text that has a shadow, and you can't see it, but it's there. And I'm not sure if you might be able to see a slight grey kind of tint over the iframe. And it essentially slows down the rendering, because when the browser redraws the iframe, it also has to redraw the text shadow. And you know, I talked about the layers, compositing layers on the graphics card. For whatever reason, this is some kind of edge case that Firefox doesn't do it in separate layers, so it has to redraw both things. So when I click on each of these buttons, the JavaScript is going to load add that ID onto the end of the URL, and then take it off again, and it's going to do it multiple times so that we can get several timings for what happens. So, okay, so you saw it kind of jiggled up and down there. So that was applying hash foo onto the end of the URL, taking it off, adding foo on again, and these are the times in milliseconds that each one took. So it took a median of 17 milliseconds. So we'll try again. So again, the page jiggled up and down, which shows that the ID did exist. Of course, the JavaScript on the page can't see that the iframe is jiggling up and down. All it can tell is how long it took for the frames to render. Okay, so I clicked on Baz there, and nothing happened, no jiggling happened, and you can see that the median is lower, it's a few milliseconds lower. And we can try the rest as well. So we can see that secret A, secret C exists, but secret B doesn't exist. And again, the JavaScript could do some calibration, so it could try this out in the document that it knew what IDs existed and which ones didn't. It could figure out the timings for a positive and a negative result, and then it can load some other document from another domain into the iframe and tell which IDs exist. So something like the SharePoint attack, which I showed you before, would be slightly slower, but it would still be possible to do that. So so I kind of showed this before. So text shadow is a CSS rule which you can apply to text, and the interesting parameter there is at the end. So this spread value controls how big the shadow is. So obviously, the bigger you make the shadow, the more time it will take to render. So if it turned out that the user has a very, very fast PC and that there was not really much difference between the positive and the negative result, then the JavaScript could just increase the size of the shadow until it got a difference in the timing. And yeah, so this is the CSS on the page. This is the element that's overlaid on top of the iframe. So it makes it essentially invisible, but it slows down the rendering. So that's one vulnerability which we've brought back from the dead. So next we're going to look at SVG. So SVG is something that's been around for years and years and years. It used to be that only really Firefox and Opera supported it, but lately all the browsers have implemented it, which makes it quite interesting. So SVG lets us do vector graphics inside of the browser. So instead of a normal image which has pixels, we can draw lines and paths and things in the web page using this XML syntax. So the reason I was looking at SVG is this thing is SVG filters, which is part of the SVG spec. So SVG by itself just allows you to do kind of flat shapes, some gradients, just basic things. But SVG filters let us apply fancy effects like this to the elements. So there are lots of different SVG filters. The spec is in the link there, so you can see what you can do, but there's lots and lots of different things. So you can apply blurs, you can sharpen images, you can adjust the color, you can do lighting effects, bump mapping, all sorts of things. And you can also combine filters together. So you can have a filter that consists of more than one element, and it will combine these things together to make more complex effects. So looking at SVG filters, you can obviously apply SVG filters to kind of lines and shapes in SVG. But there's also some interesting things you can apply them to. So inside of SVG, you can have links, just like you can in HTML. And those links can be styled with CSS. So you can have links that are different colors, depending on if they're visited. And Chrome and Firefox support that. I think IE doesn't support that. It doesn't support the coloring. In SVG, there's something called foreign object, which lets you embed HTML inside of an SVG document. So IE doesn't support foreign object. Chrome does, but you can't apply SVG filters to it. You can only do that in Firefox. And really interesting in Firefox is that they took the SVG filter spec and said, let's make it so that you can apply this to HTML as well. So you can have an SVG filter that's defined in XML, but then you can load it into an HTML document and apply these fancy effects to any HTML element. And you can do that for iframes, you can do it for links that could be colored, and you can do this for images that are loaded from another server. So when I saw this a few years ago, I thought, this is interesting. Something doesn't seem quite right that you can apply these fancy effects to things that come from other domains. So I thought, well, is it possible to do a timing attack using SVG filters? Now, the filters only affect how the page looks. JavaScript on the page can't read any of those pixels back. It can't tell what effect the SVG filter had on the appearance of an element. So it can't see what's happening. Only you as a user can see what happens. But what if we could make a single SVG filter that, depending on what element you applied it to, would take a different amount of time to run? So we have one element here that looks a certain way, and we have another element. And then we could apply this filter to that element, and it would take a certain length of time. And if we applied it to a different element, it would take a different amount of time. So I decided to have a look and see if this was the case for any filters. Now, obviously, depending on the code that implements the filter, they might take a constant time, or they might take different time. Now, in Firefox and in Chrome, SVG filters aren't done on a graphics card. They're implemented in software, which means that they can run quite slowly. But they are optimized, and they're optimized to run as fast as possible as they can. So I had a look at the source code for Firefox. I had a look at how these SVG filters are implemented. And I found that there's some interesting optimizations in there, which meant that certain filters would be faster if they ran on an image that was flat, just the same color, than on images that had lots and lots of detail. So there was some potential here for doing a timing attack. So this is what I found. This is the basis of the technique that I'm going to show you. So we have two different elements here. We have an element that is a black square. We have an element that is a white square. So see that XML in the middle there? So every SVG filter, every type of filter starts with FE for filter element, and there are different types of ones. So the first filter that we apply to both elements is this image. So what this does is it just loads an image from a file, and it replaces the element, the original element, with the image. So the black square has turned into this noise, the white square has turned into this noise. So now they're both the same. But there's a second filter that we can put in the middle there, and this is a multiply filter. So what this does is very, very simple. It goes through each pixel in both images. So it takes the top left-hand pixel of both images, and it multiplies them together. And then goes to the next pixel, and the next pixel, and the next pixel. So with a black image, all of the values are 0, obviously. So black is 0. So it's multiplying every pixel of the noise image with 0, which results in 0. And then for the bottom image, for the white image, is multiplying every single pixel in the noise with 1. So you end up with the same image again. So before we had two flat images, and now we have a flat image and a noisy image. And I found this particular filter that, when it is applied to both these images, will take a different amount of time to run. So because this is currently unpatched in Chrome and in Firefox, I'm not going to tell you which filter it is. If you wanted to go and look at the source, you probably could figure it out, but I'm not going to tell you now. So we can now bring the history stealing vulnerability back from the dead using this technique. So this is roughly how the HTML of the page would work. And I'm showing you this working in Firefox. So in Firefox, you can apply the SVG filters to HTML. In Chrome, I think they're going to implement it, but they haven't done it yet. So in Chrome, you can do the same attack in SVG. It looks slightly differently, but I'm going to show it in HTML. In Firefox, it's slightly easier to understand. So we take a link. So normally a link is text, and it'll be one color or another color. So what we want to do is take a link and instead make it into a square. So this CSS will make the link into a 100-pixel square. It will set the background color to black, and it will hide the text. So it sets the text color to transparent, so the text isn't visible. We just got a black square. And then we had a second rule, which says, for any link that is visited, set the background color to white. So now we can have several links on the page. They'll all appear as squares, and the squares will be black or white depending on if they're visited. And then in our CSS, we define another class, and this applies the SVG filter that is will be defined elsewhere on the page. It applies it to whatever element has a class of F1. So then, so we have our link, and it's pointing to a particular site. So this is a site we want to tell if the user has visited or not. We give it a particular ID, and we set this class. So the class is F1, so the filter will be applied to the link. So instead of being black or white, it will be black or noisy, and then it will have the other filter applied on top as well. And then we have a bit of JavaScript that uses request animation frame. And what this JavaScript does is toggles the filter on and off. So toggle class, each time it's run, if the F1 class is on the element, it will remove it, and if it's not on the element, it will put it back on. So the JavaScript toggles the filter on and off, and each time it turns the filter on, the browser will have to calculate all of the pixels, and it will take a certain amount of time depending on if the link is visited or not. So we do this several times and collect the timings like we saw with the frame snipping. So yeah, the element's redrawn each time we toggle it. We can take the median. And again, we can do this calibration we can do it on a link that we know is visited, that we know will be white, and an element that we know will be black that's not visited, to tell what the two timings will be. And also we can slightly speed up this attack. So We can do 16 toggles on when we're calibrating the images to get a nice reliable result. And then when we're testing the links, we want to test lots and lots and lots of links. We can just do a few, and then hopefully that will speed things up. So I have a demo of this, which will hopefully explain a bit better what I'm talking about. So link colors. So there's two things at the top here. So this is a parameter that is passed to the filter, and the higher it is, the slower the filter will take to render. And filter res is something which applies to all SVG filters, and it affects how much detail it does the filter in. So the higher it is, it will essentially use more pixels to render the source image, and it will there will be more detail, and again it will take longer to render. So I'm going to click go here. So this all runs very, very quickly, but I'll just take you through what happens. So this square here is our link, and it's basically the JavaScript cycled through each of these links and set the URL onto this image, which is the black or white square with the filter applied. So these first two links here, so these are our calibration links. The first one is the URL of the current page, so obviously that's visited. And the second link is just some made-up URL, which we know these as not visited. So, and this is the time here in milliseconds. This is the median of each run. So when the image is white, when the link is visited, we get about 96 milliseconds, and if it's not visited, we get 32 milliseconds. And then it's gone through all these links, and so you can see the timings, and obviously it knows that if the timing is closer to the high value, then it's visited, and if it's closer to the low value, then it's not visited. So yeah, that works in all of those. Sometimes it can be a little bit unpredictable if there's other stuff running in the background, but that's the nature of timing attacks. So so yeah, so we've brought this one back from the dead. So moving on now. So document.readPixel. This is a JavaScript function that doesn't exist, but what if this did exist? What if there was a function you could call from JavaScript? You could give it the coordinates of anywhere on the web page and get back the color of that pixel. What could you do with that? So you could do some interesting things. You could load a site into an iframe, a site that the user is logged into that was displaying some interesting data, and you could read pixels one at a time and see the text that was in there. Lots and lots of interesting things you could get. And normally, obviously, the same origin policy prevents sites from looking at what's in an iframe, but it would be interesting if this were possible. So could we actually do this? So the previous demo I showed you was essentially reading a single pixel. So it's reading something that's black or white in this large square. So how could we do this? How could we read pixels from an iframe using this technique? So the first thing to do would be obviously load our site into the iframe, and then we can use CSS to make only a single pixel visible. So maybe just the top left-hand pixel of that iframe, make only that visible. The rest of it will be hidden from view. Then we could somehow blow up that single pixel. So instead of taking just one pixel, it would be 100 wide by 100 high. So there's more pixels for the filter to work on. Then we would apply the SVG filter, see how long it took to run, and then we move on to the next pixel. So one at a time, we do this, the same thing that I just showed you for the link colors. We do it for each pixel in the iframe until we've built up a picture of what's in there. So I went ahead and tried this out, and it turned out it does work. There's a few little details which I found were necessary. So I found that if you apply a filter, the SVG filter, directly to an iframe, you get these kind of unpredictable results. And the reason for that is that when it's drawing the filter, it also redraws the content of the iframe. So depending on how complex the site is, lots of different things going on there, you get these unpredictable timings. So fortunately, we have these two things. So in SVG, we have this pattern element. And essentially, that lets us take some element of the page, of the SVG, and use that as a background image. So we can kind of you could do a tiling pattern. So you could take some elements and then it treats it as an image, like you can use it as a background image for an element. So that means that instead of re-rendering the iframe, we're just re-rendering this snapshot, this image of something that was previously rendered. And inside of HTML, Mozilla have implemented this thing called Moz Elements, which does the same thing but for HTML. So you can take any element on the page and you can use that as a background image for some other element. I'm just going to show you a demo of that because it's quite interesting and a little bit bizarre. So we have Moz element here. So up here we have some HTML. So this is a div with a button and a text box and a link in it. And then we've used Moz element to set it as the background image for this large div down here, and it's tiled it. So any change that we make here also happens in here, which is quite interesting. I'll just show you the source of that. It's very, very simple. So yeah, so we have this reflect element down here, and all it's got is so the background image is set to Moz elements, and it's pointing to a div with the ID of test. So that's how it works, and it turns out that this is very useful for us in doing these attacks. So in the previous thing, with the link coloring, we were using black and white images. So obviously, if we're loading an iframe, then there will be all sorts of colors in there, which we don't really want. What we want is black pixels and white pixels. So again, SVG filters come in very handy. We can apply a threshold effect so that the lighter half of the pixels become white and the darker pixels become black. So we just have a black and white image there. And to zoom into the pixel, we can use CSS transforms. So we can take an element that's just 1 pixel wide and we can blow it up so there's more pixels there. And then we can do the same thing. We toggle the SVG filter on and off, and then we see what happens. So I have a demo of this. OK, so just to explain what's going on here. So this is our iframe here. Like I said, I didn't have that much time to prepare this demo, so there's just some text in here, but this could be any website, any text from a website you wanted to read. So this is the original iframe, but it's got the threshold filter applied to it, and as well as doing the threshold, it's also inverted it. And the reason for that is because there are more, we want more black pixels and white pixels, because the black pixels are quicker to process. There are fewer white pixels, they're the slower ones, so overall it will be faster if we have mostly black pixels. So we can manually we can move this around. So the second thing down here, this is using the Moz elements and the CSS transform just to blow it up to see a little better what's going on. And it's this top left pixel which is the one that we're reading. So we can change this to a white pixel. We can test how long that takes to read. We can change it to a black pixel and test that. So you can see here, this is the median timing, and this is the individual timings of. So this is a white pixel. This is a black pixel. So now we can run this, kind of automate it. So it's doing the calibration, and then it's reading these pixels one at a time, moving the iframe just 1 pixel at a time, and reading them. So it's very slowly building up this picture. So I'll just let it run here. So you can see it's copying pretty much exactly what is in the iframe. So if this was some sort of secret information, the attacker is very slowly learning what's there. So I'll just let that run. Okay, and then the final row is all black. And there we go. So as we can see, that works very, very well. But it is a little bit slow. I mean, this probably isn't that practical to actually carry out this kind of thing in the wild. So maybe we can speed this up a little bit. Could we make some assumptions about what is on the web page in order to do this faster and have to read fewer pixels? So what if we knew the font that was being used in the web page and the size of the font? And maybe it's also a fixed width font. I'll show you why that's important later. And presumably we know exactly where it is on the page, so instead of reading a whole page, we can just read a small region of it, the region that has the secret data that we're after. So if we know all these things, what is the minimum number of pixels we'd have to read in order to figure out what text is there? So I kind of call this OCR. So normally OCR is scanning in some document for the real world and doing this kind of fuzzy analysis of it to try and figure out what characters are there. But in this case, we can be much more exact. So we know that on a particular OS, a particular font of a particular size will always be rendered in the same way. The pixels will always be exactly the same. So we can analyze a font ourselves. The attacker can analyze a font and figure out what pixels are important for particular characters, and then figure out which pixels to read. So just as an example here, let's imagine that the top right hand of that 6 character there, if that pixel was only ever set for the number 6, it wasn't ever set for any other numbers or any other characters. If we read that pixel and it's black, then we know we have a number 6. We wouldn't have to read the rest of them. That would just be a waste of time. So what we can do is kind of analyze a whole font, a whole set of characters, and we can put together this decision tree, this binary tree that tells us which pixels to read and then tells us what characters we've got. So these are just random made-up numbers here, but imagine we have a character set of 4 characters, and we might pick these 3 pixels that are significant. So we say, first of all, read the pixel that's 4 characters across and 5 pixels down inside a particular character. And remember, this is we're dealing with a fixed width font here, so we know how far to go across for each character if we know the starting position. So we read this pixel, and if it's white, we go down the left-hand side. If it's black, we go down the right-hand side. So in this case, if it's black, we know we have either C or D. So to tell the difference between a C or D, we might pick another pixel that is significant and read that, and we say, okay, if this pixel is set, then we know we have D. If it's not set, then we know we have C. So this is quite interesting, but if we did it by hand, it would take a very, very long time. It would be quite error-prone. It would be quite dull. So I decided to implement this in JavaScript to see if we could put together this decision tree for a particular character set. So doing it in JavaScript is quite handy. So in theory, what we can do is we can use the canvas element. So canvas is something in HTML5 that just gives us an area of the screen which we can draw lines onto, we can draw shapes, and we can draw text onto. So canvas is used now quite a lot for things like games and graphs, various things. There's lots of interesting canvas demos. So the first thing we do, we draw the text that we want in the particular font size and the particular, we'll draw all the characters we want out on the canvas. And then, because there's anti-aliasing, we'd apply the threshold to make each pixel white or black. We can, using CSS, we can measure the width and the height of each character, so we know how many pixels each one takes up. And then we can read the pixels for each individual character and build this binary tree, so we know which pixels to check and which characters we end up with. So I tried this. Actually, I tried it yesterday. I only just finished this yesterday. And I ran into a few problems. So it turns out that in Firefox, when you draw text onto a canvas, it uses grayscale anti-aliasing. So we just have grays, whereas normally on any LCD monitor, if you have text, then it uses the subpixel anti-aliasing. So it uses the different colors to do the more precise anti-aliasing. So unfortunately, text drawn onto a canvas in Firefox is different than text on a normal web page. So, and that gives us slightly different results, and it means that it doesn't work, which is a shame, because it meant if we could do that, we could do it on the fly. We can actually do this, build this binary tree in the user's browser, so it'd work for whatever their default font was or whatever their particular OS was. So that didn't work. So instead, I took a slightly different route. I just took a screenshot of the browser of the particular characters, and then we can load that image into the canvas, and then it has the exact pixel values we want. So just to explain exactly what I mean there, I've got another demo. Okay, so just to explain what's going on here. So this is the fonts which we're dealing with. I picked this font for a particular reason, and it's because this is the font settings that are used in the view source in Firefox. If you right-click a page, click on view source, then 13 pixels monospace is the default font. So if you look at the bottom of the page here, these are those characters with a threshold applied and blown up, so you can see exactly what they are. And what this is up here is these are kind of like heat maps. So if you look at this first box here, what the JavaScript has done is it's drawn each character on top of each other. So it starts off with a grid of pixels that are all set to a value of 0. And each time it draws the pixels over each other, it increments each pixel by 1. So these white pixels here, so no characters use those pixels, and the light greys were used by 1 or 2 characters. And these brightly coloured pixels here are the ones which are more interesting, and in particular the red. So the red pixels are the ones that were used by exactly half of the characters. So in this case, we're dealing with a hex character set. So each of these 3 red pixels were used by 8 characters. So if we take, and it's chosen this one just at random, any red pixel would have done. But in this case, this one that's highlighted, this pixel was used by these characters, so 0, 1, 2, 3, and so on. But it was not set; it was white for these characters. So the next step is that we've broken down our problem into 2. So it's taken the 1/2 that was set with this pixel, and if we look at this box here, it's done the same thing. So it's taken those 8 characters, it's drawn them on top of each other, and found the pixels where exactly 4 of the characters used, the pixels that were used by 4 of the characters. So again, this red pixel was used by 1, 3, 5, and 6. And then eventually we can go down to 2 choices. So for example, this one here, this pixel was used by 2, and it wasn't used by 0. So once we've got down to here, we've read this one, and we know if this is set, we have the number 2. So yeah, so I mentioned view source. Why is that interesting? So in Firefox, one thing you can do is you can have an iframe with a URL in it, and if you prepend the URL with view source, then instead of showing the HTML on the page, it will show you the source. So one interesting thing inside of a lot of HTML documents is the CSRF token. So this token is a secret value which is meant to be secret, and if we know this value, then we can perform cross-site request forgery attacks against a website. And what's quite interesting is frameworks like Ruby on Rails and Django actually put this CSRF token right at the top of the page in this meta tag. It puts it there as well as putting it into forms. And the reason it's there is it makes it, it's a simple place if JavaScript needs to access the token. So if you're doing AJAX requests, you can just use that meta tag to find the token. So potentially we can use this OCR technique to load this site that has this token into an iframe, and we can read the pixels one at a time. So yeah, so with the binary tree, so the question was, how many pixels do we need to read in order to determine what the character is? So it depends on the size of our character set. So if we're dealing with 16 characters, if we know we're reading a hex value, then we only have to read 4 pixels to determine a character. And if we double that, each time we double it, we have to read an extra pixel. So if we wanted to deal with just A to Z lowercase characters and punctuation, we'd have to read 5 pixels for each character. And then 6 pixels would let you read base 64. Yeah, so there's before we had to read, like 80 or 100 pixels just to read a single character. Now we can probably do it in just a few. So this brings us to my final demo, which is the one I was finishing off yesterday. So again, this is similar to the previous one. We have our iframe with the threshold applied, and we have the zoomed in version, zoom in, and the single pixel here. And this is our data that was generated by that binary tree algorithm. So we can test out, we can try this out again. So we can manually scroll this. So we can try out a white pixel. So that takes 51 milliseconds fairly consistently. We can try a black pixel. It takes roughly 38 milliseconds. Now, I will warn you, this demo sometimes doesn't work. We'll see. I finished it off yesterday. I think there's something which causes it to be unpredictable. I haven't tried it down yet, so we will see. So it's doing the calibration. Okay. That's doing all right. It didn't get the 0, but it's got the rest of them. Okay, so it's reading just one at a time here. Obviously, again, this is just a test page, a test iframe. But it's reading the characters there from the hex character set, reading 4 pixels for each character, and obviously it's much, much, much quicker than reading the whole text like we did before. So this is something that potentially is an actual practical attack. Probably would need a little bit more work than the time I got to spend on it yesterday. So yeah, so that is there's some interesting attacks there, some ODAs. So of the attacks that I showed you, the frame sniffing one, that works on Firefox. I think it could probably be made to work in Chrome, but I didn't try it yet. Reading the link colors, that works in Firefox and in Chrome. And the last 2 demos I showed, reading the pixels, currently that only works in Firefox. It might work in Chrome once they implement the SVG filters for HTML. And Internet Explorer, so IE 10, I've not tried that yet, so I don't know. So how could you prevent these attacks? So one way might be to try and prevent these different timings from happening, to make things happen in constant time. But this turns out that it's really, really difficult to do that. First of all, we're dealing with graphics here. So browsers want the graphics to be nice and fast, and they don't really want to slow things down just to prevent these kind of attacks. So we don't want to slow down performance-critical code. And even if we did decide to do this, there are factors other than our code which can affect the timing. So even if we design our code to kind of run in constant time, the compiler might do some optimizations and reintroduce these timing differences. And even if our compiler produces exactly the same code for each different case, then things like the CPU cache can affect things as well. So if the CPU is calculating the same numbers over and over and over again, it might be very, very quick. But if it's processing different numbers, lots of different values in an algorithm, then it might be a bit slower. And this is something we've actually seen. So I reported this SVG filter attack to Mozilla at the end of last year. And they have tried to fix this thing. So the particular filter that I found, they took out the optimization. And they did a test build for me, and I tried it. And the timing difference was still there. And then they went back and they made the code, they made it use kind of multiplication instead of if branches. And again, it was still there. And then they even looked at the actual assembly code that was being generated. They saw that it was, the compiler hadn't messed with it. But even then, there's still some timing difference. And possibly it's a CPU cache, possibly it's something else. I don't know. But it's really, really difficult to prevent these timing differences. So there are other ways to prevent it. So for the frame sniffing thing, for the scrolling the frame, redrawing the frame, one way to prevent it might be that if the ID, the anchor doesn't exist, if no scroll is going to occur, still redraw that frame anyway. So that might fix it, or maybe it wouldn't. So maybe redrawing the same thing again would actually be quicker than redrawing a different part of the page. I don't know. And for the SVG filter things, the SVG filter attacks, there is actually a new spec that's being created called CSS filters. And a part of that spec tries to take this kind of possibility into account, this kind of timing attack. And what it suggests is that you can't apply filters to things that come from other domains. So if you applied a filter, an SVG filter to an iframe, then instead of applying the filter to the content of the iframe, it would essentially render a blank square and then apply the filter. And the same for links. If you applied a filter to a link, it would render the link as if it were not visited and then apply the filter. So this is something which presumably Mozilla will do for Firefox at some point, and then this attack would probably not be possible anymore. So I've only really started looking at this research. You've seen I've been looking at this for a few months, but there's plenty more that could be done. I've only looked at a single SVG filter. I think there are probably lots more that might have this timing difference. And also there are lots and lots of parameters to tweak. So for a timing attack, what you want is you want the negative case, the black pixels to be as low, as quick to render as possible, so as close to 0 milliseconds as possible, and then you want the white pixels to be just enough more. So instead of 0 milliseconds, maybe 10 milliseconds. So if you can get those values down, then it will speed up the attack and make it more. It'll make it faster. At the moment, as you can see, the timings are sort of 50 milliseconds, 80 milliseconds. So it makes things a bit slower. So there's parameters to tweak and things like that. As well as SVG filters, there's a new spec for CSS filters. And these are things that are much simpler. So there are fewer things to tweak, but they're things like grayscale and blur, sepia. And these are designed so that they can run on the graphics card. So these will be interesting to test and see if we can get a timing difference. Even though it's running on the graphics card, it will be very, very fast. It's not being run in software. And finally, I mentioned that, so we're talking about slowing things down so they're slow enough to measure, because date.now gives us a millisecond resolution. If something is too quick for us, we can't measure it with date.now. But fortunately, there's this new spec which the browsers are implementing. I think Firefox has got it already. And this is performance.now, and this is designed to give us microsecond timing. So if there are things we couldn't time before, they're too quick, we might be able to time them now. So there's probably all sorts of things that are now in the realm of doing timing attacks. So there's lots of research to be done. So that's it. So my contact details. Are there any questions?